So, welcome back to the third session of the morning. It is a great pleasure to have on stage an excellent team of specialists of network reconstruction. And who else could be the moderator of this session if not Guido Caldarelli? So, without further ado, Guido, the floor is yours.
To my mind, there came 10 different names, but it's okay. No, thank you for this. Thank you for this introduction. Okay, so it's a great pleasure for us to be here today. So thanks, Stefano, for organizing and keeping in organizing these great meetings, these great conferences. There is another gap that needs to be filled in, and is the technologies, let me use this word, that we developed in these years in Lucca, together with all these persons, and Fabio nearby, you know? Can I consider you as a Lucchese, more or less? You're on periphery of Lucca, yeah. Okay. And no, you're in minority, so you have to smile, but you know, and these technologies originated from specific financial problems. And now it's the time to bring back what we found, because we believe they are pretty important for technical problems that we had to face when we started working, for example, with colleagues in Bank of England. So the problem was we never saw, actually, so let's not put everybody in trouble. We never saw this data, but we know they have data about exposures of British banks with each other. They had unaggregated information about exposures of these banks with respect to banks abroad. They don't know anything about the exposures of these foreign, for them, banks between each other. So, is this information useful to say something about the general market of these financial institutions, this general network? We believe so, and we are going to show you what we made in order to show, to give a number, to make measurements about these subjects. And of course, there have been different subtopics in that point. So this issue of network reconstruction is based, in my view, just to give you the flavor, on two basic and important ideas. One is the self-similarity of the object, like fractals. So one part has enough information to reproduce the whole, and the basic hypothesis in statistical physics, in microcanonical approach, that is that the most likely configuration, then this will happen. Now, that seems trivial, but has important consequences. Okay, so the various flavors in which this happens are the flavor of the foundational problems in statistical physics, and Tiziano, that is on my right, will explain about that. There are microscopic modeling of how this develops, and this is the first of the Fabio on my left, Fabio 1, from the periphery of Lucca. Where are you from, by the way? I keep forgetting. Pisa, yeah, in Sant'Anna. And the other, Fabio Saracco, that is on my far left, will present one of the many flavors in which networks appear. This flavor, I mean, networks can be simple networks. You can attach a weight to those networks. Those networks can be made by two different kinds of vertices. In this case, we talk about bipartite networks. Imagine people buying things on a store, an e-store like Amazon, and the stuff they buy. No? So you have two different kinds of vertices, and technicalities that you must use in order to describe these networks. I just forgot the last one. There is Giulio on my far right, and Giulio will explain how the knowledge that we have of a network now with these methods of statistical physics can be useful in order to predict what will happen in the future. I would be very sharp and then pass to the first speaker that I don't remember who's going to be, but it's going to be Fabio Saracco, that is going to tell us about the statistical validation. Okay, was there, financial networks. And he developed, in our group, is Fabio, Giulio, Tiziano, myself, and the students there, and other people there in IMT Lucca, a series of analysis of a network null model. So what's important in networks, I have 28 seconds to say that, is that networks develop certain properties that we believe are striking and unexpected. But to say that, you must know what you have to expect. And this is the work that Fabio is going to present now. Go, please.
Okay. Perfect. Before starting, I'd like to thank the organizer for the opportunity of being here. And Stefano told us to be quite brief in our presentation, so I will start with the conclusion. And this is not the last slide. It's just the first in order to outline what I'm going to talk about. First, I'm going to present this bipartite configuration model. That is a null model that is based on the maximization of entropy, so maximizing the ignorance we have about the system, but for some of the information. And we show in several papers that this null model is able to uncover some non-trivial structural properties. Then I'm going to analyze a case of study that can be of interest here, a result from Giulio and collaborators. And then how this case of study, how the application of our method can give us more information about the file sale spillover. So, okay. File sale spillover happens when, for some problems, an asset devaluates, and then it impacts on the portfolios of several financial institutions. If one of the institutions fails, it ignites a chain reaction of devaluation of different assets that have reflection on other banks or financial institutions. The problem here is that the fragility of the network comes from two similar portfolios, but the problem is in stating what is too similar. First, what is similar, and then what is too much. In order to study the system, we abstracted the structure of the system as a bipartite network, as Guido said. That is a network in which there are two set of nodes called layers that interact one with the other among nodes belonging to the same layer. Similarity here can be defined as the overlap, that is the common connection that nodes on the same layer have. Then the problem is stating how much is too much. And one way to do so is to define a null model, that is a statistical model that preserves some of the feature of the original network. So a sort of a randomization, but for some constraints. Okay, here is the philosophy. I'm not going into details. You start with the real bipartite network, and then you define a set of graphs called ensemble, in which you have all possible networks from the empty one to the fully connected. And all network in the ensemble has got the same number of nodes. Then we maximize the Shannon entropy, that is the ignorance we got about the system, but for some information. And going back to the case of study, this information is going to be the dimension of the portfolios and the number of owners of every asset. Then, as Guido said, we maximize the likelihood of the real network that we measured. We end up with, the only formula of my presentation is this probability per link. And depends on some quantities, this beta, that are defined per nodes. This null model can be used for filtering or reconstruction. Reconstruction is going to be the subject of the presentation of Tiziano, mine is going to be filtering. So, why filtering? The idea is that we got our real network, and we measured the similarity, as I said. Then, in order to say if it's enough or not, we compare the measurement on a real network with the expectation of a null model here, the bipartite configuration model. If the superposition is big enough not to be explained by the null model, the connection is filtered in is a monopartite projection that is on one of the layers. So these 4 steps. Okay, so what happened if we apply this methodology in the context of financial institution and assets? Here you can see the average degree of the validated projection on the layer of institutions. As I said, the problem is in the overlap of portfolios. If the overlap is too much, the system is less resilient. Here we see that the number of links that can be related to the average degree of nodes in the validated projection start rising, and they reach a maximum that is the least resilient configuration of the network, exactly just before the appearance of the crisis. So when the crisis arrives, the system is in the least resilient configuration measure here. Okay, here is something a little bit more in details. We can see that the different financial institutions contribute in a different way to the validated network. For instance, the highest number of nodes in the projection comes from investment and advisors, even if the biggest contribution to the number of links, which represent, if you want, the risky of the old system, comes from pension funds. And again, the number of link in the projection has a peak for pension funds just before the arrival of the crisis. If you, on the other hand, decide to project the information on the layer of securities, you still observe an increase of the number of links in the projection, with some peaks when some events comes into the game. And moreover, here, okay, I forgot to put the agenda of the last plot. Here you can see the contribution of all different securities to the number of validated link in the validated projection. And here, the black line comes from financial securities. So, going again to conclusions, as I said, we got this tool that is an entropy-based null model in order to compare real networks with some expectation, and we fix some of the information of the real network and filter it in order to understand which are the hidden properties of the network. We examined, I propose here the analysis of the files spillover, and one of the applications in which we study here is the validated projection of links that here can be related to the fragility of the network. Thanks.
And as far as understood, there will be room for questions from you later on that point. But now I have one.
Okay.
There will be time for your questions at the end of the other slides. But there is one point that I believe is a question and a comment, so probably a few seconds to discuss about that. You highlighted which are, how to say, the sources of risk. No?
Yes.
And from the data you analyzed. Is this a signal that is useful? The only one is something that can allow a forecasting of fragility, for example?
Okay, it's not, I mean, it's not the only signal that we observe using this approach, in the sense that we analyzed, for instance, the World Trade Network, and we see that the overlap of the export basket of different countries is much higher than expected in the time before the contagion of the World Trade Web from the financial sector. But there is another result from Tiziano about the risky configuration in the Dutch banks.
So we have to cut, we are on the red part.
Ah, okay.
Oh,
So,
okay.
vabbè.
Thank you, thank you. Okay, so let's pass to Tiziano that probably can leverage on these slides, because now we'll see the other part, not only the filtering, but the reconstruction. By the way, I will use this time while the people who are checking me are setting up, so the free time. All of you do know the basics about networks. What is a degree? What is, because we are using a certain jargon and it makes a lot of sense if we stop a few seconds. It's okay. If you have a problem, just raise your hand and we will try to do our work, so to explain what we do. So Tiziano, please.
Thank you very much. Thank you, Stefano, for the invitation. Basically, this talk is about, builds upon the results that Fabio showed, and it's about the reconstruction of networks. Basically, why is network reconstruction relevant? Well, the first slide overlaps with those of Paolo Barucca, but this is the starting point. Basically, it's because we have learned that in order to have a better estimate of systemic risk, we need to know or be able to guess the structural details of networks. Why? Because, well, contagion processes depend on the details, on the links between nodes. So we have to be able to know them or estimate them as best as we can. Okay, so basically an institution fails. What does happen? Well, the losses propagate to the neighbors of an institution. It may happen that some directly fails because of this first round shock, let's say. Other may not be affected immediately by these, but then because of these internal connections between these second layer group of networks, also the surviving nodes in the first step may fail in turn. So interconnections really matter. So we have to be able to estimate them. Okay, we will focus on monopartite networks. So in this case, nodes are banks, let's say, and links are exposures between these banks. Okay, so in order to reconstruct the network, we have to make the best possible use of the available information. What is the known information in this case? In the case we address here, basically we know only the aggregate information. So an interbank network is represented by these metrics. These are the single links weights, so the exposures between nodes, but we don't know them. We just know the sums over the rows and over the columns. So we only know, let's say, the aggregate fluxes of nodes. Okay, so in this case, total assets and total liabilities. How can we use this kind of information to infer the details of the network? Basically, the basic formulas of this reconstruction model is this one, which says that any two nodes have a probability to establish a link, which depends on their size, which is the philosophy, let's say, of the gravity model. But the formula is a bit different. So here, we employ the available information, which is assets and liabilities, to build this probability of connection between any two nodes. So we make use of the available information, but we have one global parameter to estimate. In order to estimate it, which is alpha here, we have to impose some kind of topological information. In this case, is the total number of links, which can be proxied in several ways. But this is the crucial step of the method. So we need to know some kind of information about the number of links, about the link density of the network, something about the topological structure. Okay, how does this method performs? Basically, if we focus just on the structural detail, so how able are we in recovering the position of the single links and also the position of the missing links, we find that, for example, here in the World Trade Web or this EMID network, the accuracy of the reconstruction, which is the blue line, is quite high. So this simple recipe is indeed relevant, is indeed effective in reconstructing the details, just the structure of the network. Okay, what about more aggregate properties that can be relevant for systemic risk? For example, the first picture here shows the size of the giant component of the network. So the number of nodes which are all interconnected and can be reached one from another. So basically, the percentage of the network that is likely to be affected by a shock. If a shock originates within this component, all the other nodes are likely to be affected. So is this percentage of nodes well reproduced? It is, because we have that the reconstructed trend, which is the blue one, overlaps with the observed trend. So if we don't know the network, we just know the aggregate information and some kind of information on the topology, we are able to recover this kind of information. The last picture here refers to the death rank, which is a measure that is supposed to give an idea of the fragility of nodes in interbank networks. And again, if we compare the accuracy of the reconstruction with the observed trend, we find again a very nice overlap. So this information seems to be enough to have a nice reconstruction of the network. What about the weights? Because, of course, it's also important to have an estimate of the magnitude of these exchanges. In this case, we adopt the gravity model prescription. So the magnitude between any two nodes is proportional to the sizes of the two nodes involved in this exchange. And we correct the recipe for the gravity model with this probability that any two nodes connect. Is this recipe effective in reconstructing the weights of the networks? Again, it seems to be so, because the recipe for the gravity model is indeed effective. So we have also a nice correlation between expected weights and observed weights. This method can also be extended to reconstruct the bipartite networks. And here we focus, and this is basically a simplified version of the bipartite configuration model that Fabio was talking about. We focus on some kind of higher order property of networks. For example, the degree correlation here are shown. The red cloud is the observed trend. The blue trend is the predicted one by the method. And we see, again, quite nice overlap of these two trends. So also for bipartite networks, this recipe seems to be quite effective. However, recently it has been noticed that it is maybe too simple. So the recipe prescribes to put a weight with probability Pij or a zero, so any known weight, basically, with probability 1 minus Pij. Can we enrich even more this model? Yes, basically by imaging that there is some kind of distribution controlling for the appearance of the weights of a link. And we just attach this distribution here. We can quite easily estimate the parameters of this distribution. This distribution comes actually from a theoretical foundation about entropy-based null model that Fabio was talking about. So there is a theoretical justification of why this exponential is here, but let's assume it's okay. Why is this relevant? Because it allows you to put some error bars on the estimation of weights. So before, we just saw the expectation, so a point estimate. Expectation and observation, they were quite nicely correlated. But here we see that we can have some confidence interval on our estimation. So we can check how many real weights fall within these confidence intervals. There are many ways of doing that, using standard deviation, confidence interval in the usual way. And again, I mean, this seems to be a quite nice result. So, just to conclude, the basic reconstruction model that we have presented here is the one encoding the idea that a node size drive the connection of nodes is related to the number of links each node establishes, only requires the estimation of one global parameter, and can be enriched to account for the estimation of errors, and can be used to reconstruct both monopartite and bipartite networks. Thank you very much.
Okay, thank you, Tiziano, and I got mine. Okay, so again, we're running slightly late. There is one comment that I would like, before we're waiting for the questions from the audience, and is, okay, now we started, and this is also a little wrap up, we started with this method that put a number, a likelihood about the possibility that one link exists between two vertices. So we saw that used as a filtering to extract information. Now with that, we reconstruct a network when we have missing information. So one question is, this method works always? There is a minimal set of quantities needed in order to do this reconstruction? It's a miracle or is it a scientific technique?
Yeah, the basic result is actually the estimation of the global parameter, and the kind of information that is really needed, is really important to achieve this high accuracy in reconstructing the network is the topological information. Basically, one kind of fundamental information that is needed is the number of links, number of connections, or some hint about it.
Okay, thank you. So let's pass to the third speaker, that is Giulio Cimini. So we saw methods to establish the probability of one link for filtering, for reconstructing. Now let's use, on
Exactly. So
this
is about application of these techniques that we saw this morning so far. And so I would like to thank Stefano. He's not here, but I would like also to thank Olga because she introduced a lot of concepts that I will use. So like about what is a central counterparty. So this work was done, now it's almost 2 years ago with the central counterparty of Italy. And so usual disclaimer applies. So the first question is, why would a central counterparty need a network-based stress test? So by definition, the market is secured by the clearinghouse. The point is that contagion might still spread between financial institutions through the market which is unsecured. And so this is exactly what they wanted to incorporate in their stress test. So an assessment of the potential losses which would be arising from interconnection which are not mediated by the central counterparty. So let me take just 2 slides to explain the stress propagation model. Well, the whole session of this morning was devoted to this. I just want to point out that we are considering here interbank lending markets, and in this case, contracts are of short duration, typically overnight. And in this case, I mean, it is known since after the crisis, that there are basically two channels through which contagion propagates. One is credit shocks, and it's the usual fact that, what's the point? Yeah. Is the fact that if a bank fails, then it will fail to meet obligations. There are also liquidity shocks which arise when a bank cannot find the liquidity needed on the market and may be needed to fire sale assets and then incurring in losses. So the traditional approach here is to basically say that losses propagate when there is a default event, then you have default, losses propagating. If you have additional defaults, then you have another wave of propagation. Otherwise, this propagation stops. But then comes the school by Stefano, which basically says that actually losses propagate also without default events. Because if a bank has some equity losses, then the obligation of these banks will be valued less, and also this bank will be likely to lend less money to the market, which then may trigger fire sales in some cases. This is the math, but basically, so through this assumption, you can build a model of distress propagation, and which is actually very simple, which is based on the leverage matrix and on the transpose of the leverage matrix for the liquidity shocks. So this is just, I mean, the two technical slides. Let's go to the application framework. So we know what a CCP is. The CCP to work needs to collect guarantees from clearing members, from banks. And these guarantees are of two kinds. There are margins and there are default funds amounts. So the default fund is well, let's say, margins are also important, but the default fund is intended to cover systemic losses, while margins are intended to cover point-to-point losses. Now, how to set the default funds well, it's an open question, because if this default fund is too small, then it will not be enough to cover potential systemic events. If it's too high, banks will be unhappy to pay for this, right? So there is regulation, of course, to set how this should be gauged, and the regulation is that the default fund should be set to cover at least losses stemming from the default of the two clearing members to which the central counterparty is more exposed. This is a rule, right? Now, how to compute this, I mean, the real amount? What they do usually is that they identify stress scenarios, they evaluate the portfolio position of clearing members, and then they compute the delta margins between stressed and non-stressed scenarios. And the two biggest delta make up the default funds. So this is a standard, well, the way they do, but you see that, so the network ingredient is missing here, and this is what they wanted to add. So it's pretty simple to add this network ingredient here, because what you can do is that you can go to the balance sheet of banks and take the quantity which refers to the unsecured exposures, use these quantities to reconstruct the network, and then use the distress propagation model on this network to assess losses. And the rest is the same, because the initial shock is calibrated in exactly this same way. Now, let me just say one thing before going to results, is that usually, as you know, balance sheets are released at quarterly frequency, right? So this means that if you employ a network reconstruction technique for 3 months, you have the same network, which fine, can work well, but you can also do slightly better. And this is what we did here. So we use a kind of Merton model to assess the dynamics of balance sheet, of aggregate balance sheets. And then from this information, we apply reconstruction. This means that we can have an ensemble of reconstructed networks for each day, basically. And this is what they are interested in because they run this exercise every day, basically. So this is just, I mean, an additional application, additional use of this reconstruction technique. Let's go briefly to results. So here you see, each line is a bank, and then this is basically, I mean, the vulnerability meaning the distance to default. Here you have default, here you have zero losses. And so in this exercise, you start with an initial shock, which is this light blue here, applied to each bank. And then you see that the network effects are really important. So second round losses are so big. If you keep on propagating, you arrive to the red situation, so very big losses. So this is the typical stress exercise. One thing that we also did is try to, well, let's say, challenge the regulation, so try to assess the regulation. So you can do a different exercise, which we call cover two shocks, in which you simply kill the two more exposed banks and see what happens. And then you see that if you do this, you basically kill these two banks, then second round losses are really huge. These two scenarios are comparable in the sense that here the initial shock is like 2.6% of total equity in the system, here is 3%. But you see that the situation is very different for the early round of propagation. So was the default amount sufficient in this case? Now, here you have 3 billion euros losses, and here you have 3.2 billion losses at the end. The default fund at that date was 3.5 billion. Enough? Yes, but because they use this cover 4 rule, not the cover 2, so they have much more resources to cover this systemic event. So the cover 2 was not enough in this case. And so you can play with this model, I mean, varying parameters, varying the initial shocks, and see, I mean, identify the possible scenarios that can arise and see if the default funds that you collected is enough. And so it was just to conclude that, I mean, these exercises are important in the context of sustainable financial system because the first ingredient of sustainability is stability. So with this, I conclude then.
Thank you, Giulio. Okay, so just one comment on the last things you were showing. So, can you say something about the policies? No, I mean from this analysis, and how much what you say relies on the parameters in the reconstruction, the information available. So
not much to do with the reconstruction. The reconstruction works quite well, and then depends really on the balance sheets that I mean, this is what banks have, and so this fact that you can infer the balance sheet composition day by day with the Merton model makes. So you have basically a continuous flow of networks in this example, a temporal flow. The important parameters are so those on which regulation can act are basically this, it's here, so this is the loss given default, this is basically, I mean, the access to liquidity that banks have. These are parameters on which regulation can act, okay. Not much on the reconstruction.
Okay, so thank you. So let's have a proper presentation. No? So apart the jokes, now we have Fabio Vanni, comes from Scuola Superiore Sant'Anna, one of the best institutions in Italy, that is in Pisa. So you are very happy that it's nearby, so we can come to you. One of the best group on adjunct-based studies, and now he will complement all these things with a microscopic view, no? of what's going on. So please.
Okay, thank you. Thank you. Yes, today I will try to express not only a series of researches or papers, but it's a summary, a story of an idea, let's say. It's about a model formation where we introduce a novelty in the rationale in which peoples or units make a connection. And this novelty is about time. Because time usually is an overlooked concept in network formation, in which we have some hidden hypothesis on that. And we stress what is the role of time in concepts like complexity, what makes complex networks, and heterogeneity in some network formation. We are building up actually a network formation rationale subordinated to an agent-based model, since we want to mimic, let's say, but it's just an application, actually, it's not the only application. We want to mimic a financial network where we have two different financial attitudes of the nodes, specific banks, where they have the leveraging attitudes according to a market-to-market structure. But the novelty of this approach is based on non-simultaneous link information. We'll see what is about. So we want, since we want to study we have the emergence of some properties like boom-bust cycles in the market without introducing so many concepts. But actually the model is very simple. The only difference is the non-simultaneously link formation. So we'll see what happens. So temporal complexity, it's the terms we used also in the recent published paper. We are trying to make other efforts about this concept. Is a new concept that is one of the marks of complexity. Okay, there are many. Usually, is related to heterogeneity of type of nodes, heterogeneity of fitness of property of some units, and etc. Also, in terms of time, we can introduce an heterogeneity of time, in the sense that we have a temporal factor that arise from which we have some anomalous dynamics that was not previously presented in an easy way, let's say. So it's connected to the stability of a system, we'll see in which sense, and the role of leverage and interaction, and also policies in a financial network. So briefly, we built this agent-based model, but it's network with the dynamic network structure, in which banks actually can create or destroy links, so very basic, according to their financial risk position, like valuatory risk or other measurement of the risk position. And we related the financial, the leverage attitudes, and so the loans between banks according to an asset in which every units are investing, according to this new scheme that is also an asymmetric information, in the sense that there is a trade-off, a connectivity trade-off between a proposer node, so there is a node, a bank that proposes something, and the other node that answer or respond to this request. So we insert just this asymmetry in the link formation that is related to a time we need to accept or not. So it's just this simple change of view. And then so a node can ask to generate a connection or to delete a link according to a position. And so we'll see that just changing this perspective, we have a natural fluctuation on the connectivity of the system, also with the onset of other properties as correlation that can be a sign of a critical behavior of the system. We'll see. And so to do that, we build up a mathematical structure where we have an heterogeneous bipartite network with two types of banks that can also change over time, actually. And a bank can increase leverage and invest in external asset if regulatory constraints are fulfilled. And the opposite, bank can close an interbank connection with deleveraging action if they don't meet a financial position. So these two attitudes, it's a natural attitude to generate or destroy links. We build up a mathematical structure taken from a new approach to stochastic process, that is an adaptation of some quantum operators to stochastic process. We did that because it was the only way to have an analytical solution, but we are not dealing with it now. And so actually we have just one parameter, that is the difference between these two types of nodes. So there are nodes that are generators and there are nodes that are destructors or destroyers of a node. And then the only formula we have is just, say, the formula for the connectivity of the network, in which we have simply delta, that is the difference between the two populations, and n is the total size of the network. From this formula, actually, you can derive a lot of properties, like phase transition, finite size effect, and to that is related, as we build the model, the price of the related asset in which they are investing. So it's very related to this behavior of this formula. Mainly, we have that for certain values of delta, this difference between two populations, we have high fluctuation, intense fluctuation of the connectivity of financial system, and also a strong cross-correlation among the two groups. And this reminds about some bar-state dynamics that usually is observed in social behaviors, human behaviors or financial behaviors that are explained also in other ways, but this come naturally from just introducing a time heterogeneity in a model, okay? And this is an example, okay? We have on the top figure, let's say, a system that goes from a very connected state, we have a lot of connection, almost full, to empty cases, so very few connections. And it fluctuates a lot according to a mean value, okay? And if we describe an event, the passage between a high connection to low connection, and we measure the time interval between these two states, we have a distribution of these waiting times as a power law. The fact that this power law is define the system as anomalous in the sense that we don't have a characteristic time scale as an exponential. We have an average time that we have to wait to have a change of the state in the system. But actually, we have what I call the time scale-free networks, because we have scale-free is related to concepts like power law, say. And this is what happens if we match the network structure to an agent-based model in which we endogenously determine what type of unit you are. You can be a generator or a destroyer according to your financial position. So we endogenously measure what type of node you can be according to the investment. So we make just this step forward, and then we relate the dynamics with an asset price. And according to, of course, some parameters that you have in the model, you can see the two typical asset price behaviors in which you have, for example, if we make some rigid regulation, so you are a generator, it's difficult to change this position because there are very rigid constraints. We have this, let's say, this two-state fluctuation in which we have boom and bust cycle. So price can be very high from time to time. You end up in another state in which we have very lower prices. Or if we make the system more flexible in the policies, for example, you can adapt your balance sheet according to some investment. You have another type of behavior. For example, here you have an average good price, good state of the market, but from time to time you can have drops, collapses, organizational collapses of the system. And of course, the distance between the collapses are distributed according to power law. So it's also, in this case, not easily, you cannot characterize as a mean time of waiting, okay? So the conclusion are that the temporal complexity in these networks is a key concept that can be useful also for further application. And regular topology should take in account this structure. We say the fact that time is not heterogeneous in a sense, at least in the way we model, And according to policies, we can target the policies to personalize care of node, since we have to neglect a reductionist approach to stability and risk, and we adopt some policies that stand on the anticipating the improbable instead of detecting the crisis, and that's the conclusion.
Okay, thank you very much. Just before leaving the ground to the questions from you, that so will be many, I have one curiosity. For the weighting distribution, the distribution of waiting times, do you have any analytical explanation of these three halves?
Yeah,
Okay.
yeah. Yeah,
we thought we had another one. So we had also. So
okay, yeah. We have make some supposition that we find that the process is a renewal process. So using renewal properties of the system, we can end up on analytical solution of the power law, also the index of the power.
Okay, we know how to will pass the afternoon, but that's okay. So now let's pass to your questions. So. A certain point will appear. Yeah, for the moment, why we? Okay.
Yeah. So my question is related to network reconstruction. You mentioned at the beginning that you showed an adjacency matrix, and that the information that we currently have is just the sums of the columns and the rows, which are, I guess, from the balance sheets of the banks, where you can read it. So when a study refers to a particular network, say the interbank network in the EU banking system, you would not be able to assume that the sums of these columns are all contained within this network, right? So the interbank assets of a particular bank will be spread across globally, not just within the network. So the question is this something you have to take into account for when you are doing such a study? So would you have to reduce the amount of the totals of each balance sheet in order to reconstruct the network more precisely?
Yes. Basically, this approach works if the total sum of the assets coincides with the total sum of liabilities. So the system is closed, let's say. Otherwise, I would say that, let's say that you can still argue that there is some connection between the fitness of a node, so that this property that drives the connection of a node, even if this condition doesn't meet. But of course, there is room for improvement. So if you know that there is some kind of external information, or not all the information is internal to the system, of course you have to correct a bit the model. Yeah.
Okay, other questions? Yeah, please.
Thank you. I have a question to Fabio. The left Fabio, Fabio Vanni. So you talked about these, don't want to be too loud. So you talked about these fluctuations in connectivity. And I, as someone who studies equilibria a lot, immediately have this question: could it be that they just oscillate around some type of equilibrium that they never reach? For example, in games, you often have a situation that an equilibrium would be that, let's say, the two of us play a certain strategy, but because of timing, we don't do that. We just oscillate around this strategy, and we just keep reacting to each other's actions. So have you looked into that?
Yes, actually, the issue of equilibrium is a very delicate point in social science with respect to physics, because here, okay, there is an equilibrium, or properly is a stationary, point, stationary state, in which we have an equilibrium value, but they but in terms of equilibrium actually is forced by the fact that the system is finite. So the equilibrium here exists because the system is finite. So you should have a stationary solution that always behave like an equilibrium. But from a conceptual point of view, the equilibrium is slightly different between social sciences of human behavior and physics, because we have some differences between the two topics. But actually, yes, the fact that we have a stationary state is because we have a finite world, at least in this case. Thank you.
Another question.
Yeah. Can I ask a bit of a question? It's a bit out there, but in the scenario that we would have another financial crisis, and maybe a very big one, because of maybe like a lot of interconnections and problems that maybe we didn't foresee, what do you think, who are the more resilient players in the economy? And I'm just thinking out of the box like that. Could it be family-owned businesses, family-owned companies, whether they're multinational or national or local or whatever, but family-owned companies, at least they have their own resources, they may have property, they may have other things which are more resilient in the economy in such a crisis situation.
Yes, can I be my guest? The spirit with which we are here today is that the spirit of our technology. Okay, so we know pretty well how a network works, how you can measure the likelihood with which you see what you see is relevant or not, and these are the things we explained. The things you're asking are more on the field of economics, in the sense we physicists, you give us one structure, we visualize, we compute, and we give back to you for your analysis. So this is, in this scenario, I will try to answer. And this I try to answer, but I would like also the other to say their view on that, these questions that we see on the slide. Which are the, okay, so I've been given a set of data, and I can analyze only this set of data. I don't know if this is family-based, what kind of business are there. I just see connections, I just see a mathematical object. It's not so clear, we are working on that, which are the topological properties that make this fragile or robust. So this is a question, an open question. So we are working. We worked together with Stefano some time ago, finding if there is. It depends on the dynamics on it, essentially. So that's the point. If the dynamics is fixed, then you can say, okay, a lot of connection is good in these dynamics. Less connection is much better in another dynamics. Healthy people, let's get together, all of us. Some guys have Ebola, you know, I stay home tonight, no? So this is the two limits. Generally speaking, I always try to answer questions. The larger is your size, the better. I mean, remember that these vertices in these networks are different one from each other. So the link, for example, are created according to the size, like in the fitness model. Oh, yes. And so, I mean, this would be my my 2 cents on that. But,
yeah, may I just add on these two questions? So, for this one on the slide, so this is, as Guido said, a work in progress also with Paolo. But so there is perhaps a work which is relevant in this sense. It's by Marco, yourself, Stefano, and so it's that if you have. So cycles are dangerous, right? So because in general, if you have a chain, you can imagine that the shocks get dampened at each step. But if you have a cycle, then the shocks come back from the beginning, and in some cases, it goes above critical threshold, then it can become amplified. So cycles are surely something which are dangerous in these financial networks. And I just want to also add to the answer. So for instance, what Fabio showed is that in the case, in the risk from overlapping portfolios, you can do some analysis like separating institution by type, and then it showed that like in that analysis, pension funds were those more risky. So you can say something like that by these techniques.
okay, so we were waiting, using 1 minute more, so relate on that. So probably just say what is a wrap up, the take-home message. There is a whole set. Sorry. So the take-home message is secret. That's why I don't use microphone. And okay, there is a substantial amount of work of years by many groups, many people in each group, based on computing and measuring topological quantities on financial networks. Of course, the use and the interest of that depends on the kind of problem that we would like, that you, not us, would like to solve. And a part of the jargon that could be, a barrier in order to use that is quite easy, the ideas that are back on these methodologies. So we'll do our best to make them as popular as possible in order to be used. This is the reason why we did that. Okay, so this is my take-home message of the whole session that we had today. I don't know if, well, I do. You want to say, add something about that? About your slides, your take-home messages, and
for what concerns network reconstruction, well, it's very important when data are missing in order to have to build realistic scenarios to run stress tests. But in general, all these methods are very relevant also when information is known, because you can have benchmarks, for example, to understand which are the significant properties that are not explained. So both when you know and when you don't have access to full information, all these technique can be very useful to both infer what is not known or assess what is significant about the known information.
Yeah, so just two things. One is about data. So because all this morning was about we need more data. This is true, of course. Still, these reconstruction techniques are useful when you want to, starting from data, you want to have confidence intervals for a measure you make on the system, like a systemic risk, right? So you have just one network, imagine that you have it, you have one value, but what does this value tells you? So these techniques to generate the ensemble of possible configuration from balance sheet data is what allows you to build the standard deviation of your measure, which is quite relevant in this context.
Okay, so Fabio Saracco.
I mean, just adding a few things to my colleagues. These entropy-based null models have, as we show, the ability of, yes, reconstructing networks when just limited information is given. But the other side of the coin is that they permit to filter the original information in the actual network and get some non-trivial insight about the nature of the system that we got. For sure, such tools should be used by policymakers in order to monitor the system and take the proper decision when all the information are obtained, I think.
Okay, so.
Yes, I want to conclude to highlight the importance of the complexity in terms also of as a temporal factor. And since we have this burst dynamics in the complex networks, we have the necessity to have a less reductionist approach to networks, also to systemic risk, moving from the predicting the time of crisis to anticipating the improbable. This also from the point of view of policy approach. Thank you.
Thank you very much. So, Stefano, probably you would like to say something or no? Okay, so we finish in time, I hope. Okay. Yeah.
5 minutes.
We are terribly scared, I have to say. That's okay. It worked. So thank you for your attention.
Thank you.
Thank you.